Hey everyone. So in the last notes, we talked about one-step stoichiometry calculations. What we're going to get into today is calculating two-step stoichiometry calculations. So what does that mean necessarily? So this we're looking at multi-step conversions. So the first thing we would do in solving these kinds of problems is we would write a roadmap, is what we'll call it. So let's say in the problem they give you moles. They give you the liters, and they want you to figure out how many atoms that is. And there's different ways we could go about this, different things that they're looking for. The easiest way to solve multi-step conversions is to do it the same way we have done prior. You can draw boxes. You could also just leave lines like you're setting up fractions. I like the boxes. It's just easier for me that way. The first thing we'll do is we're going to be given something in the problem. We are always going to start in the first box. We don't have to put anything below it. Now in our second box here, we have to determine what conversion we need to cancel out given unit. So whatever we're given, say starting out with moles, we want the bottom unit to also be moles to cancel it out, or others and so on. We have to do that in order to get to our unknown. We'll do the math, we'll solve it, and then we can go and check our work. So the easiest way to go about this is just do some practice problems. So first example here, how many grams of oxygen, O2, are in 3.23 times 10 to the 22nd atoms of O2? Again, we're going to start with how many atoms we're given. So we're going to put 3.23 times 10 to the 22 atoms of O2 in our given here. Now notice input boxes, and again, you don't have to. Under practice worksheet, I use boxes. I just like to separate my stuff that way. Boxes, lines, these both mean the same thing. It's all conversion factors. Go to the problem. I'm going to have a given here. Now, the question's asking me how many grams. Now, before I can get to grams, I have to make sure my units cancel out so I can get there. So here, I can figure out how am I going to get from atoms to grams. Okay, so I'm over here. Particles, same thing as atoms, ions, molecules. I've got to go from here to moles. That's my step. The arrow is pointing this direction. So I know I have to use Avogadro's number here. Then for moles, I go to grams. So second step. I know that for every 1 mole of O2, there is 6.022 times 10 to the 23rd atoms. They left out the extra 2 there. It won't change your answer too much if you do that. So I got to get rid of atoms. Again, this 1 mole of anything, this could have been 1 mole of a grilled cheese sandwich, 1 mole of that, it doesn't matter. 1 mole of anything is this atom. So 2 is Avogadro's number. So that's my first conversion factor. Moles will go on top because I need atoms to cancel out here. Now, some people like to go ahead and solve this. I wait till the very end to solve. So let's do it that way since we'll do one big calculation. All right, I've got my step here. Now I go mole math. Now I'm going from mole to grams. So I'm going to be using this conversion factor here, and I've got to use tells me to use the periodic table. So I've got to figure out how many grams is in 1 mole of O2. Well, O2 is a diatomic molecule, meaning I have 2 oxygen atoms within that molecule. If I go to a periodic table, I know that 1 mole of oxygen is 16 grams. Periodic table tells me that. So 2 moles would have to be 32 grams. So for every mole of O2, there is 32 grams. And moles has to go on the bottom because we want this mole and this mole to cancel. Now let's look back at the problem here. Atoms have canceled, moles have canceled. The only thing I have not crossed out is this little g here. The reason why is because that is what I'm solving for. Now I can go back in math. So 2 ways you can do it. You can multiply 3.23 atoms by these 2 fractions, or the way I also like to do it is you can multiply this number 3.23 by everything top and then by what's on do it is up to you, but those are two different ways you can solve. If you want, go ahead a moment and try both those ways and see if you get the same answer. So when we calculate this, we find out that there are 17.2 grams of oxygen, O2, in this many atoms, O2. Which, if you look at the number, it makes sense. 1 mole of O2 is this many Avogadro's number. 3.23 times 10 to the 22nd is about half that much. So if 1 mole has 32 grams, about half of that should be about 17.2. So the answer is logical. Let's look at another example. So this one's asking me to find volume. The question says, find the volume of oxygen, O2, occupied by 14 grams of O2 gas. So they give me grams here, and I need to get to liters, which is a volume. So let's go on that. So I'm going from grams all the way to liters. No, I got to go from grams to moles first. So I'm going to use 0 points from grams to moles. So 1 mole every X amount of grams. Well, we're going to do here. So I'm going to write my given. Given was 14 grams of O2. And again, I've got to have 1 mole on top because I'm going from grams to moles. Cancel out. 1 mole of O2, determined it was 32 grams. So our grams will cancel. Because we need to get moles first. And then once we do that, we need to figure out how many liters that is, the volume is. So I'm going from moles to liters. Well, this tells me that for every 1 mole of anything in the world, there is 22.4 liters of that. So my moles need to cancel. I'm going to put 22.4 liters of O2 on top, moles on the bottom. So grams cancel, moles cancel with just liters. So if I take 14, multiply it by both of these conversions, I should get 9.8 liters of O2. Another example, this is going from, looks like we're going from molecules to grams. So let's find mass. Well, mass is always grams of O2 when we're given 1.22 times 10 to the 23 molecules. Just to let you know, molecules, ions, particles, atoms, those are all, they all mean the same thing. You're up here under the category. So I've got to go from molecules to grams. So start from here, I got to go back here. So it's kind of like the first one we did. So to get there, I've got to use a number. So I'm starting out with molecules. I need molecules to go at the bottom of my conversion factor so they cancel out. For every 1 mole of O2, there is this many molecules, Avogadro's number. And then I'm going to multiply it by what I'm looking for. So I know for every 1 mole of O2, this is pretty much identical to the first problem. We've just changed atoms or particles to molecules. They're interchangeable. So if I multiply this out by my conversion factors, I should get 5.4 grams of O2. Okay, the rest of the notes here for these 30 versions, that's honors only. We will pick up the notes again when we get back from this extended break we're having, if we get to come back. We'll pick up talking about limiting reactants then. For now, honors, stay tuned. I will post an additional video for 3 steps.